Okay, hello everyone, and welcome to this presentation, which will be about intrusion tolerance as a two-level game. So we consider a distributed system that consists of a set of service replicas, which jointly provide service to a client population. And we want this system to be intrusion tolerant in the sense that even if an attacker compromises a subset of the replicas, the system as a whole should continue to operate correctly and maintain service to the clients. This problem can be understood on a high level through the following picture, where on the x-axis you have time and on the y-axis you have the system performance. At some unknown point in time, indicated by the dotted line, an intrusion event may occur. And when this happens, we want that the system maintains some acceptable level of performance and as quickly as possible recovers to normal performance again. Examples of systems that have these kinds of requirements include power grid systems, real-time control systems, as well as any kind of system that deal with monetary transactions. So for example, banking or e-commerce applications. And if we look at the main mechanisms behind building an intrusion-tolerant system, they have primarily been developed within the areas of distributed computing, reliability theory, and cryptography. By contrast, this presentation will be about how we can leverage game and decision theory for intrusion tolerance, and how we can use those theories to build even more reliable and more cost-efficient systems. In particular, if we look at state-of-the-art intrusion-tolerant systems as of today, they consist of three main building blocks. Firstly, you need to have an intrusion-tolerant replication protocol that allows your replicas to coordinate themselves and reach agreement on the response to a client request. Secondly, you also need to have a replication strategy that tells you how many replicas to use. And obviously, the more replicas you have, the more failures you can tolerate, but that also implies a higher cost. Finally, you also need to have a recovery strategy, because irrespective of the number of replicas, if you run your system long enough, then eventually all of them are going to fail. Despite this fact, traditional intrusion-tolerant systems did not do any recovery and only used a fixed number of replicas. Then around the year 2002, we had this seminal paper by Castro and Liskov, which introduced the idea of proactive recovery, where you recover your replicas at periodic time intervals. And most of the systems developed after this paper was published follow the same idea. So they also use periodic recovery and very simple heuristic replication strategies. Now, the main question that we are interested in for this presentation is, can we do better than these heuristic control strategies by leveraging game-theoretic reasoning and optimal control? And to answer this question, we propose the following control architecture, where we have a set of nodes that are coordinated through a consensus protocol, and each node is segmented into two domains. So we have a privileged domain, where we run a controller, and then we have an application domain where we run a service replica inside of a virtual machine. And the controller then monitors the replica and decides when to do recovery, where recovery simply consists of replacing the virtual machine with a new one. In addition, there is a system controller that manages the replication factor and performs failure detection. And we say that this system provides correct service to the clients if every request sent by a client is eventually executed, and each healthy replica executes exactly the same sequence of requests. Now, by introducing some standard assumptions on the synchrony of the network, we can then guarantee that the system provides correct service as long as the number of failed nodes is upper bounded by f, and the total number of nodes is at least 2f plus 1. Now, the main insight behind our game-theoretic model that I will soon present is that meeting these two invariants correspond to two control problems. So the first one relates to intrusion recovery, and the second one relates to replication control, where we need to make sure that we do recovery quickly enough so that we never reach the threshold f, and we also need to make sure that we have a sufficient number of replicas to meet this inequality here. And we formulate these two control problems as a two-level game, where on the local level, we have node controllers that perform intrusion recovery. And on the global level, we have a system controller that manages the replication factor. So before I dive into the model, let me just start with the assumptions behind it. And we make three main assumptions. Firstly, we assume that the probability that the system controller fails is negligible. In our architecture, the system controller is actually not reachable to the attacker, which means that it can only fail by crashing. And therefore, we can meet this assumption in practice by simply adding some redundancy to the controller. The second assumption is stronger, and that is that compromise and crash events across nodes are statistically independent. This assumption means that the nodes have to be geographically distributed so that power outages and those kind of failures become independent. And furthermore, we need to run different software and different operating systems on the nodes so that with high probability, they do not share any vulnerabilities. Finally, since we do not know what the attacker knows about the system, we make this standard game-theoretic assumption that the attacker knows everything. So it could be an insider, for example. And based on these assumptions, we then model the local recovery game as a partially observed stochastic game with two players. So we have the controller and the attacker, each of which can take two actions. So the controller can either do recovery or wait, and the attacker can either decide to attack the node, or it can try to deliberately generate false intrusion alarms in order to trigger excess recovery and thereby achieving denial of service. The node can be in three different states. It can be healthy, it can be compromised, or it can be crashed. This state, however, is not measurable to the controller, which only can measure some noisy observation of the state. For example, some alerts or log files. Based on these observations, the controller then computes the so-called belief state, namely the posterior probability that a node has been compromised given the history of observations. And since the state here is Markov and the belief is a sufficient statistic of the state, we can then define a recovery strategy to be a mapping from the belief space to a distribution over the action space. And when selecting this strategy, the goal of the controller is to balance two conflicting objectives. So on the one hand, it wants to minimize the time to recovery. As soon as we suspect an intrusion, we would like to do recovery. But on the other hand, we also want to minimize the frequency of recovery, because each recovery incurs a cost. And we also add in a safety constraint here, which we call the bounded time to recovery constraint, that the time between two recoveries have to be upper bounded by some value delta R. And if we now compute the optimal cost function for the controller, J, then we can see that it is piecewise linear and concave in the belief, as predicted by the theory. But more interestingly, we also find that it has a certain threshold structure, where the best response for the controller can be characterized by a single threshold value, alpha, such that when the belief is below alpha, then it is optimal to wait. And as soon as the belief or the probability of compromise exceeds alpha, then it is optimal to trigger the recovery. And the implication of this structure is that we can compute the best response for the controller very efficiently by directly parameterizing the strategy with the threshold. So we effectively transform a complicated dynamic programming problem with a very high-dimensional strategy space into a simpler parametric problem with a one-dimensional strategy space. And then we can simply learn the threshold using standard optimization techniques, for example, Bayesian optimization or stochastic approximation. And by doing that, we are able to reduce the time it takes to obtain a best response compared to dynamic programming with around 2 orders of magnitude, depending on which optimizer we use and also depending on the value of delta R. So that gives us a best response, but let us now also consider the equilibrium analysis. And the equilibrium that we consider for this game is the perfect Bayesian equilibrium, which puts 2 restrictions on equilibrium behavior. Firstly, the strategies have to form a Nash equilibrium in every subgame. And secondly, the beliefs of the players have to be updated in accordance with Bayes' rule, and they have to be consistent with the observations from the game. And we show in our paper that our game has such an equilibrium. And furthermore, in a very special circumstance, this equilibrium is also unique and pure. Namely, when the controller has perfect observability, then the equilibrium is unique. And the approach that we use to establish this existence theorem is as follows. First, we consider the case when the time horizon of the game is fixed, and then we show that we can convert our stochastic game into an extensive form representation, and therefore it has a value. And then we consider the limiting case when the time horizon approaches infinity, and using an argument based on the discount factor, we are able to show that also in that case, the game must have a value. This value can then be computed using the heuristic search value iteration algorithm. And here I've plotted the value of the game in function of the intrusion success probability of the attacker. Now recall that the value of the game from the controller's perspective is actually a cost. So as you would expect, when we increase the probability of an intrusion, the value of the game also increases. And in the extreme case that you see to the right, when the probability of an intrusion is 1, then we have a very simple equilibrium, where pure equilibrium actually, where the attacker will always attack and the controller will always do recovery. And which is quite intuitive, I think. And that leads to an average cost of around 1. Now, when we compare the equilibrium strategy to the periodic recovery strategy that is used in current intrusion-tolerant systems, we find the following. So on the y-axis, you have the average cost, and on the x-axis, you have the KL divergence between the observations during normal operation and during an attack. So essentially, a larger KL divergence means better intrusion detection. And what we find is that if you do not have any intrusion detection, then the equilibrium strategy and the periodic strategy are equally good. However, as soon as you have some intrusion detection signal, and by no means does it have to be perfect, then the cost of the equilibrium strategy very quickly goes down. So in conclusion, if you have an intrusion-tolerant system where you have some intrusion detection capabilities, you have some sensors for measuring data, then there is a significant gain in using a game-theoretic recovery strategy as opposed to a periodic strategy. So in summary, the local level of the game consists of node controllers that perform intrusion recovery, and we model each of the local recovery problems at every node as a partially observed stochastic game. And now we'll move on to the global level, where we model replication control. And we model or formulate the global level as a constrained stochastic game, again with two players, the controller and the attacker. And we define the state of the game to be the number of healthy nodes as estimated by the controller. So if you consider the figure in top right, you can see that at every time step, the nodes send their beliefs to the system controller as sort of a heartbeat. And therefore, the system controller always has a global view of the number of healthy nodes in the system. And based on that information, it then decides whether or not it wants to add a node. Note that we never need to remove a node because nodes will naturally fail over time. At the same time, the attacker is deciding which nodes to attack. And here we consider Markov strategies that are mappings from the state space to a distribution over the corresponding action space. And when selecting the strategy of the controller, the objective is to minimize the number of added nodes, because adding a node incurs a cost to the system. But at the same time, we need to ensure that the service availability is greater than or equal to some chosen value epsilon. And you can see in the table here how the value of epsilon translates into allowed downtime per year. So for example, if we choose epsilon to be 3 nines, then we only allow for 8 hours of downtime. And by defining the game in this way, we can now analyze the reliability of our system from a game-theoretic perspective. So in particular, we know from the previous proposition that the system provides correct service as long as we have 2 f+1 nodes. This means that we need to have at least f+1 healthy nodes, and as a consequence, the mean time to failure of the system equals the mean hitting time of a state in the game, which is less than or equal to f. And here I've plotted the mean time to failure in function of the number of nodes, and as you would expect, the more nodes we have, the larger the mean time to failure will be in general. But really the key insight here that I want to convey is that we can analyze reliability of the system by simply looking at the sequence of states in the game, which forms a Markov chain. And if that Markov chain has a stationary distribution, and if the service availability constraint is feasible, then there always exists a best response of each player that can be computed using linear programming. And the key behind this theorem, or the key behind proving it, is that finding a best response can be formulated as a constrained Markov decision process in our game. And therefore, the theorem basically follows from standard results in Markov decision theory. So here is the mean time to obtain a best response for the controller for different sizes of the system. And we can see that even for very large systems, like 2000 nodes, we can obtain a best response in just a couple of minutes. Now for the equilibrium, here we consider the Markov perfect equilibrium, which requires that the Markov strategies have to form a Nash equilibrium regardless of the initial state of the game. And it was proven by Altman 20 years ago that our game has such an equilibrium. And the proof is based on some linear programming concepts and Kakutani's fixed point theorem. But unfortunately, even though it exists, there is no algorithm really for computing it, no efficient algorithm. And even not that many algorithms for approximating it either that are very practical. And complexity-wise, it has also been shown to be p-pad complete to obtain the equilibrium. Which of course means that in general, it's going to be intractable to obtain the equilibrium for this type of game. However, as you may have noticed, our game has a very special or quite simple structure, which actually enables efficient computation of equilibria. In particular, we show that the best response for the controller is always going to be decreasing in the state. So the state here is the number of healthy nodes in the system. And clearly, the fewer the number of healthy nodes you have, the more likely it should be that you add another node. And that's very intuitive, I think. And then it means that there actually exists a dominating strategy for the attacker that always just tries to minimize the number of nodes, healthy nodes, regardless of what the controller is doing. Sorry. And that actually means that we can obtain an equilibrium of the game by computing the best responses independently using linear programming. So here's a comparison between the equilibrium strategy and the heuristic strategy that is used in current intrusion-tolerant systems. On the x-axis you have time, and on the y-axis you have service availability. So what we can see is that if your system is just going to run for a short period of time, then it doesn't really matter what replication strategy you use. You could equally well use a fixed number of replicas and not change it, or you can use adaptive replication. They are basically the same. But if you're going to run your system for a long period of time, you really need to do adaptive replication in order to ensure service availability. So in conclusion, if you have an intrusion-tolerant system that is going to run for a long period of time, and you have service level agreements that you must fulfill, then there's a significant gain in using a game-theoretic replication strategy as opposed to a heuristic strategy. So to summarize the model, it is a two-level game. On the local level, we model intrusion recovery at every node using a partially observed stochastic game. And on the global level, we model replication control using a constrained stochastic game. Now to the evaluation. We do the evaluation on a testbed that we have at KTH, where we have a rack of servers connected through an Ethernet switch. And these are really commodity servers that are like 20 years old and probably not worth more than a couple of $100 each. And on this cluster of machines, we then implement the system architecture that we saw earlier. So just to remind you, this is the architecture that we implement. So each node here then corresponds to a physical server in the rack. And on each node, we of course run the controllers, but we also run a service replica inside of a virtual machine. And in our case, this is a very simple web service. And for the consensus protocol, we implement the min-BFT protocol, which is a standard protocol for intrusion-tolerant systems, has been around for almost 15 years. And there are many other protocols that we could have used as well, but we chose this one just for simplicity. I'm not going to go into details of this protocol here, but if you're interested, there are more details available in the paper. And when we implement the protocol, this is the throughput that we have of our implementation. And the reason that I'm showing this figure is it's not that our implementation is particularly fast, it's just to show that the general trend we should have for any consensus protocol, and that is that the more nodes you have, the lower throughput you will have in general. Because the more nodes you have, the more messages you have to exchange in order to reach agreement and to reach consensus. So this really motivates the cost function that we defined in the global game, if you remember, where the cost function was defined to minimize the number of nodes. And that makes a lot of sense if you look at this figure, because the fewer number of nodes we have, the better throughput we can expect from the system. To evaluate the system, we then basically run intrusions against it, and then we try to measure and see how well it tolerates the intrusions in terms of service availability and in terms of operational costs. And we consider 10 types of intrusions for our particular evaluation. And you see the intrusion steps listed here in the table. Now, to make intrusion detection non-trivial, we also run background services on the replicas to generate some noise in the network and some false intrusion alarms. And here you have the corresponding empirical distribution of the intrusion alarms from the testbed for each of the 10 different types of attacks. So in blue, you see the distribution during normal operation, and in red, you see the distribution during an attack. Well, we can notice that these distributions overlap, which indicates that there is quite a lot of false alarms. But on the other hand, we can also see that it's a pretty good signal for detecting the attack in all cases. Finally, here are then the evaluation results, where the brown and red bars relate to our game-theoretic strategies. The blue, green, and pink ones relate to the baselines that are used in current intrusion-tolerant systems. So if we start from the left, we can see that in terms of service availability, there's not a big difference between the game-theoretic strategies and the baselines. There's a small difference in our favor, but it's barely noticeable in this figure. And I think the reason for this is just the way we designed the evaluation scenario. If we would have ran the evaluation for a longer period of time with many more attacks, I think we would have seen a more clear difference on availability than what we did in this case. On the other hand, if you look at the middle column, then you can see that in terms of average time to recovery, we have a very clear difference. The game-theoretic strategies achieve a significantly lower time to recovery than the baselines. This is quite expected because the baselines, most of them are based on periodic recovery, which means that they always have to wait an entire period before they can trigger the recovery. Whereas our strategies, by contrast, are based on feedback control. So they can trigger the recovery whenever they suspect that there is an ongoing intrusion. And finally, if you look at the rightmost column, you can see the recovery frequency. And there are two things to note here. Firstly, the recovery frequency of the game strategies and the baselines are more or less the same. They're very similar. You could have expected that since the time to recovery is much lower for the game strategies, that the recovery frequency will be higher, but that is not actually the case. And finally, we can also see that the recovery frequency of the equilibrium strategy is a little bit lower than that of the best response, which sort of indicates the exploitability of the best response in the sense that it allows the attacker to trigger some excess recovery. Although in our particular evaluation, this number of excess recovery was lower than I expected. So in conclusion, we have presented a game-theoretic model of intrusion tolerance. We have established several structural results regarding this model. We have computed the equilibrium and evaluated it on a testbed, showing that we can significantly reduce the operational cost of state-of-the-art intrusion-tolerant systems. Thank you very much for your attention.